All right, well, we'll get started. So welcome to the Always Connected, Always Seeing webinar with Edge Impulse and Sony. We've got David Schwartz here with us today to give a technical deep dive on using Edge Impulse with Sony's new Spresense 4G LTE board, and to show how you can build cutting edge computer vision applications that leverage always connected IoT sensors. So a little bit about David. David is a user success engineer at Edge Impulse, helping customers build and deploy products powered by machine learning. He is a University of Texas graduate with previous experience in embedded systems design and application engineering. You'll also see Armagan Ibrahimi from Sony online with us today. Armagan is a partner solutions engineer at Sony, and she'll be helping to answer questions throughout the event as well. So the first 45 minutes of today's webinar will include a presentation and demo, and then the last 10 to 15 minutes will be open for questions. So if you do have questions during the webinar, there is a Q&A section at the bottom of your screen. You can open that up and type your question in there, and David and Armagan will answer as many questions as they can before the end of the webinar. So thanks again for joining us, and I'm going to let David take it from here.
Thanks for the introduction, Katie. Hello, everyone. So today we're going to be talking about developing ML applications and using the kind of always connected nature of 4G to add extra capabilities and features. This is specifically in support of the Spresense Developer Challenge, which is going on right now with deadlines to request for free hardware to enter the contest by May 20th. This contest has a host of prizes from both Sony and Edge Impulse. And from our side, we're specifically really excited to look for innovative and interesting uses of edge machine learning with the Spresense platform and all of the capabilities that it provides. So in support of that, what I really would like to accomplish in this talk is provide, first off, a kind of general overview and idea of where can, TinyML, machine learning, AI sort of applications practically help you develop an application or product with something like the Spresense as a hardware platform. What additional capabilities can that add to your product? And then we're going to, from that general example, dive in a little bit more specific to the kind of problem set and solution or reference solution that we've put together, which is a always connected wildlife camera running on the Spresense with the 4G LTE board and doing on-device and remote classification using the Edge Impulse platform. So without kind of any further ado, we'll go ahead and get started. And I'll finally mention, put any questions in the chat, and we'll have plenty of time at the end to get through, anything you're curious about. So to start, what is, the TinyML, the Edge ML, the AI kind of buzzwords, and what do they mean? What do they kind of practically map to when you're actually doing product prototyping or product development, as you'll likely be doing if you enter into the Spresense Challenge. And so the real way to think about this is that this is just kind of an acronym, and what we're really talking about is intelligence and awareness. And in this context, what we want at a very high level, abstract from anything that you're specifically trying to build, we want our products, our devices to have an understanding of kind of what they need to do and make kind of the correct decisions in order to kind of achieve that goal and do so efficiently. This isn't unique to machine learning, AI, or anything like that. It's just kind of that general, the device and the product is capable of performing the task that it's meant to do. And to give some specific examples where we kind of see kind of on the Edge Impulse side, a lot of the ML sort of exciting use cases, you'll see things like taking photos and kind of classifying what that photo is, early warnings of things going wrong, either in a kind of safety critical application or an industrial application, or kind of monitoring and handling different types of data and kind of deriving novel results from that. And so the artificial intelligence, the Edge AI, TinyML, it's just mapping this contextual awareness to an embedded device like the Spresense. So you don't need necessarily, and this is, well, as we'll get through an exercise that's really important to go through, you don't necessarily need to kind of throw AI, ML techniques at every single problem. There's plenty of tasks out there for kind of IoT platforms and devices like the Spresense that you'll be able to completely solve with traditional programming. And where we kind of have seen a lot of development, where our users have found a lot of value using Edge Impulse, is at kind of the point at which this traditional programming model breaks down or starts to struggle a little bit, given the constraints of what the end use case, the end device is attempting to do. So in the traditional kind of programming model, you design an application, you might do some sensor processing algorithms. You might say, oh, I'm going to, when I see a signal come in, I'm going to kind of just classify, just say, okay, when I see a rising signal, I'm going to start, executing my code and processing that operation. And that works fine in a low noise environment with this very simple case. But there's lots of situations where even with what seems like they would be very simple tasks, and we'll get into specifics in the next slide, you'll see a kind of difficulty in how do I approach this in a traditional programming model? How do I encode the possible tree of kind of different types of images, different types of audio signals, different types of time series sensor signals that could be captured by my device? And how do I handle that when it's out in the field, when I'm not able to really interact with it, when I'm not able to really monitor it? And so the kind of ML workflow, rather than just writing normal code to solve problems like this, is to take a very data-centric approach, to look at this as a problem of how do I build up a representative data set that describes the context in which this this device, in this case the Spresense camera, is going to be kind of deployed in, is going to be observing. And then how do we from there, from that set of data, how do we categorize it, slice and dice it up so that it represents the interesting events, the interesting things that we're looking for? And so with the kind of last bit of genericness here, the strengths of this approach, of this kind of data set based training system rather than rules-based programming, is that you don't need to sometimes fully understand exactly the minutia of the kind of implementation details of a certain class of sensor, a certain class of signal, in order to get some sort of contextual awareness and intelligence up and running on your target device. A great example of this is in the biometric space. IR sensors measuring heart rate, pulse are very accurate. They're used by medical devices as well as smartwatches. And that's a sensor problem that has been solved with traditional processing. But to do so took a lot of research, a lot of development and focused expertise on the specific problems associated with IR data and human interface. So when we hit new novel problems, when we see the next one of those, sometimes it can be a faster kickstart to just start taking a more data-centric approach and look at, okay, can ML help us here? It can also deal with ambiguity better than rules-based programming often. And it can often, if you build up your data set right, can be very robust to noise and low amounts of kind of signal data in what you're getting. Now, on the flip side, in order to do anything in this scenario, you actually need a starting point of data. You need quite a bit of kind of examples to start with, no matter what you're doing, whether it's images, whether it's audio, and anything that you don't have a representative sample of, your model, it won't be in kind of the universe of what your data set can model. And as a result, you often will have discrepancies between what you expect, the performance of a learning algorithm to be and how it actually behaves. And usually this is due to a gap, a subtle gap or issue in the data set, and where it kind of where its contextual awareness is versus where it's currently operating. And then finally, this is algorithm dependent, but in computer vision specifically, which we're kind of focusing on in this webinar, there's often a little bit of kind of a question mark of and this is baked into the last point too, is why did the model arrive at the result? And usually that's in the context of incorrect results. Why did the model not recognize what I expected it to, and why did it work properly in a very similar image? That's the sort of thing that can be a difficult, in certain applications especially, a difficult problem to deal with if you don't have that discernible and consistent workflow. How do you actually reliably deploy something and into the real world if you don't have a strong understanding of how it's going to behave? And so we actually do this with our customers when we're evaluating, hey, like what would be a good approach for developing, is machine learning a good fit here? There's a lot of development and interest in developing edge machine learning applications, but we want to kind of qualify that and determine what's the value proposition here. What do we have to gain from adding these sorts of ML algorithms at a high level, and then we can map this to a specific problem. And so the acronym that, as far as I know, is coined by our internal ML team lead, Daniel, is BLERP, which is bandwidth, latency, economics, reliability, and privacy. If you look at kind of the lay of the land here, you can take these kind of general sets where we've seen EdgeML be very effective. We can go through a kind of case study and determine how that will apply. And then we can say, okay, now that we think that this might be valuable, what's a good systematic approach to start solving the problem? Because it's not always the case that you're able to just collect a perfect data set that represents exactly what you need in your end application. Oftentimes, and almost entirely, especially with sensor data, with embedded devices, remote deployments, that's the most challenging part. So how do we frame the problem? How do we approach these practical concerns? And let's go through a kind of tangible exercise here, so we avoid I avoid just talking continuously in kind of abstract. And the fourth thing, actually, I forgot to mention, it's very important, is ethical analysis. We want these applications to do good in the world. We don't want either by mistake or by intention these sorts of ML algorithms to cause harm. And so we want to kind of analyze, hey, what are the ethical concerns? How do we balance that with potential use cases? And we'll get into a specific example where we can kind of see how we approach this sort of thing. So in that specific example is a wildlife camera. So generally, it's been very common for the past kind of over decades for biologists, wildlife researchers, and other groups to deploy remote and kind of standalone cameras that use motion sensing to detect the presence of an animal and snap a photo. It's used to passively kind of monitor the kind of number and population of different species in different areas. And that can be used for both conservation efforts as well as managing, land developments, protecting threatened species from poachers. And with this kind of space, there's enough interest in it that you start to hit some scaling issues as you try to deploy for a research group, a conservation organization, many of these cameras across a large area of land. The kind of first main problem is that motion sensing is inherently not actually what you want. You want photos of specific animals that you're looking for, or any animal, depending on exactly what research you're doing. And the PIR sensor will end up giving you a lot of false positives, which is both kind of a practical constraint. Okay, now you have to look through 1 million images in order to find the useful ones. But then also those extra camera cycles and extra storage requirements can damage, how long you can keep these devices in the field, how often you have to service them. In addition, you have to actually go out and get these devices. If you're doing a kind of standalone non-connected sensor, you have to physically go retrieve them. And if you're intentionally, looking for kind of a diverse set of wilderness areas to do this sort of sampling for, again, a research group, conservation group, that's naturally going to be very difficult. And then with the expense associated with that, of course, expense with kind of memory and kind of a difficult sweet spot to hit in terms of, okay, how often do I collect this sort of thing? And the constraints are really interesting. These devices are battery powered. They need to be deployed for months at a time. So they need to have a really, really low current consumption. These are very remote devices. So generally you're not going to have much high bandwidth connectivity, which is why originally this SD card based static approach was kind of the way things were done. And in short, it's a difficult problem that feels like kind of almost immediately that, hey, like maybe some of this AI ML techniques might help here. And so, this kind of is an easy one-to-one mapping, but okay, bandwidth constraints and potentially even not zero connectivity constraints. The EdgeML kind of classifier will remove those false positives, or hopefully remove a large set of those false positives from the data set and leave you with less data to transmit, less data to store, and a much higher allowance to kind of potentially go get your data as well. So this kind of pulls into doing the same analysis for adding 4G connectivity, where we say, okay, if we're comparing this SD card based approach to a connected camera, well, now I can do my research. I can deploy a bunch of cameras out into the world, especially in North America. A lot of areas have some amount of cellular coverage, even far out into kind of the unpopulated areas. And so you can get that connectivity while still, and speed up kind of the pace of your research, lower kind of the overhead of sending people into the field. Kind of the initial impetus for this among most of the researchers who kind of did the first pass on these wildlife camera traps with AI/ML acceleration is just removing the millions and millions of empty images that they don't care about, they don't want to sort through, they don't want filling up their SD card, and just kind of causing them inconvenience. And then this one actually at the very end is kind of an approach for the kind of ethical side of things. If you're looking at these sorts of devices, you might be in a situation where, hey, I want to collect pictures of animals, but there's also a hiking trail here, and you don't want to necessarily be, collecting and monitoring data of people. And so one of the advantages of EdgeML is you can do that sort of classification locally. You can say, hey, these are hikers. This isn't, a bear or whatever I'm looking to classify. And then from there, just discard that image, and it never gets transmitted into the air. You don't waste bandwidth. You don't risk any privacy concerns. And so in this way, this is a great application for EdgeML. And in fact, it's a very popular one. We have some of our own internal and partner projects going on, building out different flavors of these sorts of wildlife cameras for different use cases. And so let's look at what it looks like to actually go through and build this sort of thing with the Spresense platform. And I think it's really interesting because the platform has a lot of very unique features that, especially for this type of remote deployed application, work together very, very well. So, what do we need? We need some sort of, quality image sensor. We need connectivity in remote areas. Basically, the more time we can have connectivity, the less work the users of this wildlife camera have to do. But we still at the same time want to be able to function if we lose connection for a short amount of time, or if we're in an area where, for whatever reason, that connectivity, isn't present. We need low power consumption. We need to be able to operate off a battery for months at a time. We need on-device storage. So even though we're going to be transmitting data, like I mentioned earlier, sometimes you might lose connection. We need the capability to store things on the device when needed. And then we need to be able to run small machine learning algorithms to do some of the empty photo removal and classification that we'll go into a bit more detail on in a little bit. And the Spresense can do all of this. The kit you get with the kind of 4G LTE baseboard gives you all this capability built in. I mean, you even have some really cool extra features that can be really helpful for certain types of data sets. So with built-in GPS, you have the ability to grab contextual information about, hey, where was this sample collected? Which is really useful because as we'll see when we go into kind of the live demo and we look at our data and kind of how we approach building algorithms to kind of work well with a wildlife camera, we'll see kind of why location dependence might matter a lot. And additionally, from the software side, okay, we want to be able to capture data from the device when we have connectivity, but we don't want to waste that bandwidth, especially since LTE remote sort of far from cellular towers, you might not have a very high bandwidth kind of connection. And there might be kind of costs associated with deploying lots of 4G LTE devices at scale that are doing data streaming. But when possible, it would be great to stream live data from the device. It would be great also, like I mentioned before, to capture when and where we took that sample. And we want to eventually build towards, and we'll get into this in a bit more detail, an approach where we can start deploying these sorts of devices into the field. We can start collecting data. And then we can kind of tweak our algorithm as we go along. We can add more samples. We can build up a better and better algorithm to kind of do classification. And we want to be able to do that pretty easily, pretty seamlessly, right? We want to say, okay, this can't be a thing that requires us to kind of go back to bring all of our devices in, put a new model on there, and deploy it back in the field. This is something that needs to be relatively easy to prototype. And this will allow us to kind of solve that problem I alluded to at the very beginning when we were talking about limitations, where we might have situations where the place we deploy a wildlife camera to isn't well represented in our existing data set. And then we get incorrect classification results. So in those situations, the solution, the way we want to kind of frame the problem to solve this, is to be able to use this telemetry data that we're streaming off the devices to build better models when we identify that those issues kind of occur. So just to go into the components, the specific components in a bit of, not too much detail, but just kind of to get an idea of kind of what we're working with here. For the camera, we're using the new HDR camera module for the Sony Spresense, especially compared to kind of a lot of off-the-shelf CSI2 and MIPI cameras. This specifically has really good low light performance, which is fantastic for kind of wildlife camera situations where we're going to be, potentially running at night and we want to still capture, nocturnal animals. And it also slots right into the existing kind of Spresense kit and device. And so we can kind of use the existing ecosystem of examples, right out of the gate. We also kind of want the 4G LTE modem and connectivity. This is kind of the compute, and this the Spresense actual CX device is going to be running inference, as well as handling kind of shuffling data from the SD card to the cellular networks, calling the Edge Impulse APIs. And so we want to kind of have that compute capability on hand while still not blowing up our power budget. And then on the 4G side, we want to be able to transmit over wherever we are. We want to have good coverage of and connectivity where possible. So on the connectivity side, along with the board, you'll set up and you'll receive, if you kind of follow through. I'll have links at the end for this, and buy the full Spresense 4G LTE kit. SIM cards that allow the device to connect to cellular towers across different networks. Sony's partnered with two SIM card providers. They have TruePhone as well as Soracom. And so for both of these, the regions and exact kind of feature sets and it might differ slightly where, which one is kind of the best choice. There's also some interesting, for both platforms, data telemetry options outside of kind of the training data set side, more on the device management. Hey, where is this device? How long has it been deployed? How often have I seen it go dark over time? And kind of tracking that sort of thing effectively can be really helpful. Again, if you're more later down the road trying to deploy a lot of these into a large area, for research purposes or something. So with those kind of components put together, and again, that's kind of all baked into the Sony kit. Well, what's our actual approach? I'll mention the source code for this is going to be fully available online as both a reference, some documentation on exactly what's going on, and kind of how to approach using it. But I think for kind of an understanding of what's going on, you need a bit more than just the firmware view. You need an idea of okay, what's happening between our platform, our connectivity layer, and then our actual kind of sensors. So basically, the workflow is like this. We have an HDR camera and optionally a PIR sensor. So we can either wait to see motion or we can just continuously sample if we maybe have the power budget for it. On the Spresense device, we then run our TinyML classifier, which this classifier that's running on device, as we'll see in just a little bit, is a very simple classifier. Its only task is to determine if an animal has been detected or if it's some other class that we really shouldn't care about unless we're doing some debugging and kind of data collection telemetry work. So this constraint on minimizing what this on-device model needs to do just says, hey, I just need you to detect if an animal is present or if the PIR sensor detected a tree, moving in the wind or something like that. And that, is going to, and cuts down on, 95 to 99% of the images captured, just right there. And then, with that kind of filtering process, we now are in range where it's completely reasonable to send low resolution, in this case, 96 by 96 resolution images through the 4G modem. Now we're going to be sending these and we're going to be doing all the device management and interfacing directly through Edge Impulse. And so Edge Impulse provides some very simple APIs where on the Spresense device with the connectivity enabled by the modem, you just have to make an API request, a POST request to our web services. And you can just throw data at your project and upload new samples. As you'll see, we'll also be able to live classify samples. And this is really powerful because it means that in addition to this very simple constrained model that we can kind of get reliably functioning well, we can add and kind of prototype and build up different models and approaches and algorithms in the Edge Impulse platform. We can do this remotely, and we can also verify that this algorithm, how this algorithm would function in the field using a kind of hosted remote model that we kind of store in and interface with in the Edge Impulse platform itself, but that's being fed live image data. It's being fed, the proper kind of sort of only animals samples, only good data, basically, within some kind of constraint around what this small on-device algorithm is able to do. And this has worked really well. This sort of dual kind of remote and on-device classification approach is very common, especially in the past when on-device inferencing and on-device machine learning algorithms were less common. But even here, besides compute constraints, just practically, we don't necessarily want to have to continually update our model when we have a limited amount of bandwidth. The model size might be quite big, hundreds of kilobytes. And the bandwidth and data constraints on the 4G side really make that kind of on-device continuous updating not really feasible, at least at the frequency that we would like to do when we're kind of in this prototyping and model development step. So let's, without further ado, let's kind of see, like what exactly does it look like kind of on the at least on the model side for here as to, what we're working with. How does this look from the Edge Impulse side? What can we do on the continuous modeling side? What does this look like on the API side? So fantastic. So the first project we have here is the actual training and development of the on-device classifier. So that's going to be, hey, what are we actually running on device to detect this is an animal, or this is a car driving by, or the wind just blew the wrong way, and so we need to ignore this sample. And the data we're collecting is from a fantastic compendium of kind of wildlife camera nature data sets by LTE. This group has also worked with a bunch of different kind of research groups and organizations to collect millions and millions and millions of images from all across the world. And the only kind of challenge is, okay, what do you include? How do you not get overwhelmed by this kind of huge amount of data at first? And then how do you actually map it to real world performance? Because the quality of these data sets are fantastic, and highly recommend the sources and public project links for the Edge Impulse project, as well as the raw data are available. You can tweak and kind of modify these for your application. And the main question is, what do we constrain to strike the balance between the size, reliability, and kind of iteration time on our small on-device classifier? And what do we wait to kind of do later? What do we wait to kind of push off on that kind of model that we're going to spend some more time collecting real world data, comparing it with something like the LTE data sets. And in this case, what we've done is we basically collected roughly a kind of 10 to 15,000 image benchmark data set from a North American Caltech study. And that's kind of what we've used to kind of start this on-device small classifier. So if you look at the data here, what we can see is we can kind of go and we can look at some of the kind of animal samples, and we can get an idea of kind of what our actual kind of space of kind of data that we're getting from these devices looks like. So this is a mix of RGB and color images. There's different kind of aspect ratios, camera sensors, resolutions. A lot of times, as you can kind of see here, the bird or the animal in sight is very hard to see, especially kind of when it's zoomed out like this. And so kind of, okay, how do we start, investigating how this data set will perform when we try and train it? And so the Edge Impulse platform actually provides a lot of really cool tools for this. One of the new things that we're soon releasing, and we're really excited to show, is what we call the Data Explorer. And the idea of the Data Explorer is that even before you've tried and attempted a learning technique, even before you've gone and said, I know, ahead of time, I want to use a neural network to solve this problem, we can get an intuition on kind of the clustering and relationships between different samples in your data set, intuitively, purely based on kind of either DSP-based visualizations like we're showing here, or based on a pre-existing network or the in-progress network, whatever you're kind of developing and iterating on in the projects itself. So this first view here is showing just traditional DSP. So this is just running some signal processing and doing some statistical analysis to say, hey, how could I cluster the different samples in this data set? And you get some really interesting results immediately on doing this. So there's certain samples of cars that appear to be kind of very neatly clustered, separate from a lot of different applications. And that likely has to do with kind of a very different signature for a large portion of the image, as you can see here. It's completely occluded by the car. You can kind of see that clustering represented naturally. And we don't even need the neural network kind of representation to see this. Additionally, we can, even with the Data Explorer, start to look at unlabeled data. And we'll go into this a little bit more later. So these are some samples, a mix of samples that I've collected from some prototype Spresense devices, as well as some other non-North American data sets to kind of highlight this point. And they're all imported into the project as unlabeled. And you can kind of see some natural clustering of these unlabeled kind of data sets. If you look through here, a lot of these samples are of kind of the same site where a camera was mounted, and you can kind of see a few animals coming and going throughout different frames if you kind of analyze this cluster. But we don't want to cluster this based on whether, where the camera was. Oh, I zoomed in while Zoom streaming slows things down a bit. We want to classify this based on the classes that we're looking for, right? And so what we can also do is we can go back and we can regenerate this visualization, either based on a generic image classification model using a lot of standard classes. We use, if you're familiar, kind of COCOS based models that kind of do 90 generic image classes. Or we can use the trained impulse in our project if we've kind of gone through this before, and we have here. So I'm going to kick this off and let this kind of generate. It does take a few minutes to run because it's sampling and classifying like 20,000 samples or something like that. But we'll come back to that in a little bit, and we can kind of see how it handled that unlabeled data as well as kind of what our model performance looks like in general. So on the impulse design side, there's a lot of interesting approaches that we can take here. So, we have this data, we have this initial idea of, okay, there's some natural relationship between these different classes that I could see in the pure DSP-based clustering visualization that we do. And then from here, you might want to say, okay, well, I might want to try some specific types of DSP, some specific types of learning algorithms, or I might not have any idea like what I want to try at first. Maybe this, I just no clue. And so the platform will give you suitable defaults based on the type of kind of data that you're bringing in. And it additionally supports, if you're kind of using our enterprise grade platform, one really cool thing that we do is we support custom DSP. And in the space of wildlife cameras, this can be really powerful. In particular, we're not using it in this specific project, but with certain sensor types, certain environments, some pre-processing that might be bespoke to the location or exactly what you're trying to do can be very powerful. So as an example here, I'll just throw in edge detection so we can kind of see what that looks like. And then we won't actually train off of this. So I want to kind of get through this. I realize I'm running a bit slow on time here. But basically, as we kind of look through this, we trained this on around 15,000 samples of data. That's combining the training and test sets. And we're able to get a really high accuracy, at least, and we'll see too, similarly good accuracy in tests on detecting animals, which is mainly kind of what we're concerned about here. If we have, a few extra percentages of non-empty data, especially in this kind of iterative stage, that's okay. But we really don't want to miss, good samples of animals, especially if those animals are rare. The way that we actually arrived at finding a model that kind of fits onto the Spresense's device constraints that we mentioned earlier around power, around running kind of all of these multiple tasks simultaneously along with this inferencing, and in this case, being very sensitive and picking up the animal presence with high accuracy. Because we actually used our Eon tuner. And so the Eon tuner is really cool in that if you kind of take that approach of, I don't know what model I want to design, I just want to kind of follow the platform defaults. The tuner is an AutoML tool that lets you kind of search the space of different model architectures, different DSP techniques available in your project. And you can basically go through this. You can configure your device constraints as well as kind of some advanced features if you kind of are familiar with the sort of AutoML tool sets. And you'll actually be able to get a whole slew of different attempts with different resolutions, different color bands, different neural network approaches. And you'll be able to get both the on-device latency, the RAM, ROM usage, the accuracy across all the different classes. And we can even check out the test accuracy of these models as well. And so, what we look at here is that when we kind of get into it, we end up selecting a model for this kind of neural network block based on a prior run of the Eon tuner that met our device constraints that we configured. So kind of these top 3 performing models, or the first few of them, a lot of them exceed our latency requirements. And then also is very accurate at classifying specifically this this animal class, which is kind of our most critical one in this specific application. So from here, okay, we can actually, one of the things we can do, which is really interesting, is we can now test this before we even have to go deploy it to the Spresense on live data. So here I'm grabbing an example from not North America, and where we're, North America, US specifically, I should specify, where this is just some kind of open source data, and the sample has been classified against exactly what the same model that's running on the Spresense kit in kind of the firmware example. And we can see how it behaves in a new environment. And here it worked pretty well. But if we kept going through these, we would doubtlessly find areas where the model falls apart and isn't able to handle that new environment. Or just completely misclassify something even though it is in the environment. So if we want to do that kind of at a more holistic level, we can just classify our entire set of test data as shown here. And when we do so, we'll see, it might take too long to run. Yeah, we'll see this has still pretty acceptable accuracy, and then we can get some kind of intuition on what in our feature explorer, which we'll return to now, on where we were struggling. So back in the data exploration view, and we're almost through with most of the cool stuff here, so we can kind of continue. Now we're looking at not the DSP-based approach, but the full kind of model and the clustering kind of relationships and mapping that our neural network, that this algorithm that we trained is trying to kind of basically relate these different samples to one another. And so and that's a very kind of high level kind of description of what's going on behind the scenes. If you're familiar, this is using kind of the neural network's embeddings, so like lower but still hidden layers in order to kind of give you this mapping. But we see that now, if you compare to the prior one, almost all of these car samples mapped very, very nicely to a very specific cluster or two. We still have very kind of close clustering based on location of this Micronesia-based kind of few example images, as well as hidden in here some other kind of more spread out images that I collected from live data, as well as from other data sets, where these samples are, this kind of geography-based mapping implies that, hey, this model, the data that we just brought in is quite different from a lot of these North American samples, which is fine. That just means that, hey, if we want to deploy this in this environment, we'll need some more data. We'll need a more robust kind of way of understanding how, what different animals look like in these two locations. And so building on that, using this sort of capability to go in and explore our data set, being able to kind of click, pull in unlabeled data and kind of just apply labels, we've gone ahead and built a species classifier that we're kind of iterating on that takes this and really tries to make use of that continuous learning capability. So right now, this model has around 16 or 17 species. Again, mostly based on North America and mostly the US. And, there's still some certain classes where there might not be very much data, like foxes. There's only one example of a fox, and it's getting presumably miscategorized because of that. And other samples that might be kind of getting misqualified, but overall, we're still hitting around 82% validation performance, likewise 80% test performance in kind of the similar range, with a much larger set of our kind of potential space of camera trap data from Leela, and this is trained on about 50,000 images in comparison. And we're able to use the data explorer to kind of iteratively add new data sets and go categorize them if it's unlabeled data, if it's has a different labeling scheme than kind of what we're presumably used to. As an example, if you had a very granular classification between things, and now you kind of want the generic, this is a squirrel versus the North American red-tailed squirrel or something. And so this is kind of, both these projects are public, and they're fully linked kind of in the slides, which I'll kind of go back to now. And this kind of is basically kind of the end result of kind of a few early iteration cycles of that system diagram that I showed in the previous slide, where we're doing this kind of continuous learning. We're building out a model that won't just be able to say that's an animal. It'll be able to tell you within a specific region where, what species that is. So getting back to kind of the core of this, we want this to kind of serve as a starting example of the types of things that you can do with the Spresense platform, along with Edge Impulse embedded ML kind of capabilities. You can sign up joining the challenge through Hackster directly here. We have kind of free hardware available with a deadline for May 20th to kind of submit an idea on, hey, this is what I want to try and make. Like I mentioned before, Edge Impulse specifically will be have separate prizes for TinyML, EdgeML sorts of applications that we find interesting. So full resources in this slide deck will go out for reference. All of the source code for actually running on device in an office scenario, it's hard to kind of pull in live data for this sort of thing. But the source code's available with kind of documentation and guides here. Both public projects are available, so you can just grab and iterate on either the species-specific classifier or the generic one. And then we have a discount code for hardware if you end up buying your own through Framos, and this gives you the full kit, everything in the components view to kind of make these sorts of computer vision applications. And then the final thing I want to mention before we go to Q&A is that we have Sony specifically has a follow-up webinar on this that'll be doing a bit more LTE specific kind of design and development help. So make sure to check that out. If we didn't really have time here to go into kind of the full details on exactly how that works, so I think this would be a great follow-up on exactly, kind of the nuts and bolts of kind of making LTE and cellular connectivity work. I jumped to the link. So with that, only running a little bit over time.
You're doing good. No worries. We have a few questions. One from Brian: does Edge Impulse have any tools to help in labeling of custom data sets? For instance, a user-friendly tool to label images, and is that labeling saved and exportable?
Yeah, so this works differently depending on the type of image project that you have. If you're doing classification-based projects, you can use the Data Explorer, just as I kind of was. What I didn't kind of finish clicking through in this example is you can, if you find a cluster here, I can go ahead and I can just set a label. Here I'm just going to set it based on location. Doesn't really make that much sense in the context of this, but it'll actually automatically go in and kind of classify an automatic kind of k-means generated clustering. So in images, this can be a little bit, you'll need kind of a starting network to go from. You won't really be able to do this on pure DSP. But in audio and sensor applications, we'll see people kind of go through and you'll just be able to click through and label clusters of people saying different words, different audio sounds, different sensor samples, and you'll get kind of, large swaths of samples covered very quickly. On the object detection side, switching to just as a quick example of this and object detection, just in this case, we're doing classification because that's really what we need for a wildlife camera in this context. But in this, in object detection project, we have a labeling queue that will let you kind of upload data very easily, draw bounding boxes, and then you'll be able to export everything out in a kind of JSON labeling along with the raw images format. And so this is completely, you can export this, and it's the same kind of image format that I believe the TensorFlow object detection sort of examples generally use for bounding boxes as well as labels. And then is there anything else I wanted to talk about there? And so then on the custom code side, so unfortunately, that'll have to kind of stick to a little bit more of the exploration of the of kind of running this on device. But generally what we do on device is we do baked into our SDK, into our deployment options. Let me switch to the project I actually want to show deployment for. We include full profiling code. So with the Spresense specifically, you can either output just the C++ library to use with the Spresense SDK standalone, or as we're doing for this specific project, we're using the Arduino IDE or the Arduino SDK for the Spresense. We can export an Arduino library. It builds into the Arduino's kind of timers, and you'll get a line-to-line count of exactly how long object detection takes, and you can kind of use that sort of telemetry to get an idea of kind of what you're doing in code. In the actual example that we're doing here, and this is kind of glossing over it, we're using GPS to get the location and time that the image was taken. So we're not having to use the on-device, like we don't really care about super granular tracking, but we know within the minute that the sample was taken, and we know generally where. And then I think that's all for that question. Hopefully that covers everything.
Awesome. All right. So another question from Nielsen. So the platform cover from edge detection to training and deploy. Can you tell more about custom code, like on the device counting the time between the last object detection or performing an action based on a detection?
Yeah, and so I kind of accidentally kind of moved into answering that one a little bit at the end of my prior answer. But yeah, just to kind of, yeah, it's basically we have that kind of in the timing, but then also in this case, we're taking the advantage of the Sony GNSS positioning to get the accurate time.
Gotcha. All right. Martin had mentioned that 10.5.6.5.8 gives user not able to access.
Yeah, I'll have to look at that after this. We'll have to see. Maybe it might be the case that that's an incorrect link, or that we'll need. But we'll fix all of that before we send out slides after this, and the slides will have kind of all the links, and I'll make sure that they're all working properly for everyone.
Great. Awesome. From Garrett, how do you determine what models can run on the Spresense with its constraints?
Yeah, so that's and I kind of sped through this. This is exactly what the Eon Tuner is kind of intended for. So the idea here is that you look at a given device target, and we have support for kind of any fully supported device, but here you can basically configure for the Spresense at whatever latency requirements you need to hit. Here we're pretty flexible on this, so it's kind of set to a second, but a lot of situations inferencing once a second is a little bit low. So with those constraints in mind, we'll do an estimate based on some profiling we do in the platform to kind of guess and get a rough idea of how long a given algorithm will take to execute, as well as the memory and RAM and ROM requirements. The only thing to mention here that's really important is you have to take into account other memory requirements of the rest of your application, because the Edge Impulse platform doesn't really know, like, oh, I'm pulling in the 4G LTE stack, I'm pulling in all these different camera drivers, I'm pulling in other code. And so I might, my actual ROM usage, even if it shows as being, oh, I'm only using 10% of it here, that might actually be kind of of critical importance. So that's something you kind of end up needing to track a little bit on your own, but you'll at least have that kind of starting point of, okay, I have an idea of what I'll need, and that it won't be, in this case, larger than the entire available memory on the Spresense or something crazy like that.
All right. This one is from Timothy. I am facing a problem and searching for an answer. Suppose I build an ML model and deploy it on device and install device at a remote location. Later, if I improve the model on Edge Impulse, how can I update the model on the device without reaching it? Any suggestions?
Yeah, so this is, classic firmware over-the-air update sort of problem. If you look at the way that the Edge Impulse library deploys for both Arduino and normal C++ projects, what you'll basically get if you use all of the optimizations available is you'll get compiled C++ source code for everything, including your model weights and the neural network implementation. So what that means is that in that situation, if you want to deploy an update, you need to do a full firmware update, right? You need to rebuild your binary. You need to have some sort of bootloader in place for that given, target. Armageddon, maybe you can speak if you have details on like bootloader support on Sony's side. I'm actually not familiar. I can't say. we can kind of from there go and build the full application. The alternative, though, is you can also, if you want to keep the model architecture the same, if you say, okay, I think this approach, this convolutional neural net will work, but I want to add more data laden. One thing that you can also do is you can disable the Eon compiler. This, instead of in code, leaves the data for your neural network implementation in a bit more of a portable TF-Lite sort of format. And then it can be a lot easier. There's some custom application code needed. So this is the kind of thing where you, in practice, you'd probably need to kind of reach out to us and get some support and kind of at least to get started on something like this. But the buffered model, this sort of non-Eon compiler model, can be more portable. And then you can leave all your application code the same, and you just have to be able to fetch and replace your old model weights and kernels with your new one. So that's an option. For specifics, it'll kind of go into exactly how this sort of process works and stacks and all of that are available in the Spresense. And what I'll say specifically is for this Arduino-based example, the Arduino libraries over-the-air update capabilities are a bit limited. So this is something where for on Spresense, you might need to drop down and kind of not use this sort of Arduino first firmware example in order to kind of make sure that you're able to do these sorts of firmware over-the-air updates. Yeah, I think that's everything for that one. Awesome,
thank you. All right, we've got a couple that came in prior to the webinar. Let me grab a couple of those. I think this one is by low power, can this work on solar and battery, and how small an energy budget can it work on?
Yeah, so in low power in this context, this means low power in terms of I can give this device the equivalent of a, if I give this device, an 800 milliamp hour battery, it'll last for months, right? Which is relatively large in the space of embedded systems. But to be completely honest, this is a kit prototype. We're not using custom hardware. There's, in a lot of ways, we're kind of using a lot of power to do transmissions, run inference, and these things relative to the space of super low power, like energy harvesting, whether from solar or from sometimes even like radio. This is maybe a bit higher than that. However, at the same time, with a large enough solar array, absolutely. And really the intent with this sort of setup is more in the range of this is consuming kind of milliamps of current over time, more if it needs to transmit. And then that's enough in this scenario from some kind of initial early tests that, you can plug this into a power brick, you can plug this into some small form factor source of power, and you'll be able to kind of leave it deployed out in the field for quite a long time. Hopefully that answers that one well.
Awesome. We'll have time for one more. Let's do this one. How to add custom sensors to gather data from Sony Spresense.
Sorry, could you repeat that actually? I think
how can you add custom sensors to gather data from Sony Spresense?
Yeah, so the way custom sensors work, we actually provide this sort of example primarily in the Arduino libraries, if you're interested in taking a look at this. So what this looks like, it's 2 steps. So the first step is similar to uploading any sort of data. You can use, if you're working over 4G, you can use the Edge Impulse kind of API to upload data. And the API doesn't care about where the sensor values came from. It just will take an arbitrary buffer of samples with some metadata on what's there. So you can define that in code, build out kind of use whatever sensor drivers you have available, fill a buffer of data, and then use the Edge Impulse APIs to upload that. Now on the inferencing side, you'll get a model out from Edge Impulse, and we have some examples of, hey, what does it look like to classify time series data in the Arduino library specifically? So if you grab this deployment and build it, you'll get some generic models that show, hey, this is what it looks like to run inference with any type of sensor data from a static buffer in memory. And so then from there, the only thing that you'll need to do is fill that static buffer of memory with actual real sensor data rather than what the demo shows, or what the example shows as a kind of starting point, which is a fixed pre-written buffer, just for kind of simplicity and testing sake.
Awesome. We're up on our time. So thank you so much, David and Armagon, for joining us today. And for the demos, I posted a link to the contest in the chat, as well as Edge Impulse's discussion board. If you do have questions that you didn't get answered today, definitely go check that out and ask your questions there. We will be sending out a follow-up email in the next couple of days with the link to the recording, as well as all of the great information that was shared today during this session. So thanks again for joining us, and I hope you all have a great rest of your day.
Thank you.
Take care.